Right, the stack. Without the stack, we cannot actually write any programs that have procedures and functions. It is fundamental. In fact, it's so fundamental that the CPU has direct built-in support. Interestingly, we never mention this register when we talk about the CPU, which I think is a bit odd. There you go. Right, we can think of the stack as a list of memory locations. A stack, a literal stack, like a stack of plates. Okay? And that's an important thing to think about. We use the stack of plates analogy because the way that this data structure works is you only access the top of the stack. Just like in a stack of plates. Unless you're crazy, you would not try and grab a plate from in the middle of a very large stack and pull it out. You get the one that's on the top. When you put a plate on a stack, you stick it on the top. That's how a stack works. Okay? It's nice and simple. We can use an array to hold the stack. And we visualize these stacks as a structure that grows upwards. Okay? And shrinks downwards. In reality, in most CPUs that I've ever programmed, the stack actually goes down from the top of memory. Alright, but we visualize it this way. And when we're building them, we don't care how it's physically stored, we just use an array. So, you just need a reference to an array, which we'll call stack, and we need one index, the stack pointer, which we often refer to as SP. Okay, stack pointer. The stack pointer, in general, and it's up to you when you implement these how these work, but in general it makes sense that the stack pointer always points to the free space on the stack. So in this case, the stack is empty, and what we've got is the stack pointer is pointing at the first location, position 0 in the array. So if I want to put something onto the stack, I place it at the location that the stack pointer is pointing to. Okay. There are two operations, well there's three, but there are two main operations that we use on the stack. One is to put something on the stack, and the other is to take something off the stack. Okay. So, these have got two distinct names. And they're not as crazy as the names that we call the Q ones. But to put something on the stack, we call it push. Push a value onto the stack. So if we was to write this as a procedure, so we're just doing pseudocode here, we'd want to push an item onto the stack. Something we want to save. That's what a stack's for, it's for saving stuff. Okay. To remove something, we call it pop. Doesn't need a parameter, we just return whatever's on the stack. It's a function. So the process of the stack is actually quite straightforward. So if we want to put something on the stack, we need to look where the stack pointer is and place the item at that position. Okay? So all we've got to do, if I'm going to call my stack, I can say stack to refer to the array. The index I want is the stack pointer. And then I'm going to store the item. Nice and easy. Okay? So once I've put an item, so let's assume we're going to put, I don't know, the number 45. So using this notation that I've just written, we're going to put 45 there. Everyone happy with that? Yeah? Right. That is no longer the top of the stack. Where is now the new top of stack? 1. 1 above. So what do we need to do to the stack pointer?
Increment it.
Yeah, increment. So we can just put, in our short form, we can just put SP++, which means increment. If you want to be giving the person at the other end the best chance of marking it, you might want to put that. Okay? But I'd be concerned if the person at the other end doesn't know what SP++ is. But there we go. I'll leave it as that. Right, so after I push this item, the stack pointer now is there. So it's at the free space. A lot of these data structure algorithms, it makes sense for the pointers to point to free space because you can do things quicker, you can make calculations easier, and you'll see in a minute. Is there any potential problems with this stack? So what the logic I've just written, it seems to work. We add a new item wherever the pointer is pointing and then move the pointer up.
Runs out of memory.
Right. Stacks are finite. Because they're in memory, okay, they're competing with everything else that's in memory. So they cannot have an infinite length. On the Atari VCS, which had 128 bytes of RAM, I kid you not, 128 bytes of RAM, that RAM was for all the variables of your games, okay, so 128 bytes of RAM, and it had to be used for the stack. Okay, and the programmer's manual for the Atari VCS said, set the stack to the top of memory, byte 127, put your variables at the bottom of memory, starting at location 0, and just write your program so the stack doesn't go into your variables, because it will do. 128 bytes of memory. And people have written, people are still writing programs for the Atari VCS, even though it's over 40 years old. And they're doing ridiculous things. 128 bytes of memory, ridiculous programs and games that people are doing on that machine. It's phenomenal. But that's an extreme example of you don't want the stack to run into other things. Because it will do. It will run, it just keeps increasing. So we need to monitor. So at the minute, in my code, I've got nothing doing any checks. I'm just automatically putting some onto the stack. So I need to do a check. I need to check to make sure the stack's not full. Right. With the little diagram I've got, how many items can we store in the stack? 6. So the max of this is 6. I mean, actually, that's the length as well, isn't it? The length of the array that we're using. Okay. Now, in pseudocode, and this is different in languages. Languages do it differently. But in pseudocode, how do we specify the length of an array? Or ask for the length of an array?
Array.length.
You can do array.length, or what's another one?
Length.
Use a len function. Yeah? At what point, based on that 6, what would the value of the stack pointer be if the stack is full?
5.
It'd be 6. Wouldn't it be 5?
Oh, yeah.
If it was 5, it'd be there, which meant, oh, actually, that's the last available space, isn't it? When the stack pointer is incremented and ends up there, it's going to be 6, isn't it? So when it's 6, or when it's the length of the array, the stack is full. Now, we've got the job of designing and writing this stack code. We don't care whether that screws up the program that is using the stack. We just say, tough luck, mate, it's full. You decide what you're going to do once the stack's full. But it isn't our responsibility, we don't care. This is how you should write programs. You say, right, I've got some functionality I want to build. Let's just worry about that. Don't worry about how it's going to be used. That's irrelevant to us. If you start trying to get bogged in with what this stack is being used for, then you've gone completely off track. And you won't actually be able to write the code. This is one of the skills that you've got to develop. This being able to decompose things to their raw elements and then build the raw elements. When you then pull it all back together, you're using those elements. Okay? Because when you've got raw elements that you've built, you can test them. And you can like say, right, let's really exhaustively test that this stack works. And then when you come to use it in projects, you can be pretty sure it's going to work. It's nice and simple. The code is simple. Right, so we need to do a test. So really, we need to say, if the stack pointer is less than whatever, let's use this format, len of stack. Could have called it max stack or something, but you'd have to then say to the example what max stack was. So as long as the stack pointer is less than the length, so all these positions are less than 6, then we can update the stack and add something to the stack. If we then put an else, we then need to indicate to the user that we were not able to put something on the stack. In reality, when you're programming, there are 2 ways you could do this. You could return, even though this is just a procedure, we could make it a function and have it return true if it was successful and false if it wasn't. So we could do that, okay? Or what we could do on modern systems, we can throw exceptions. Now we've not talked about this, and in the future we will look at exceptions, but maybe not at the minute. Okay, I'm not going to elucidate on that. Right, so the other thing that we could do is just indicate that the stack is full. This is pseudocode, so we're not saying how it's done in a particular language or how the programmer should implement this. We'll just say this is the logic you need to follow if you want to implement push for a stack. So we could just say output, whatever that vaguely means, stack full. Not that I have ever seen a program where if you tried to put something on the stack and it's full, you would output text, but hey. Okay? You're showing the example by doing that you're saying, like, there is a condition where we can't put things on the stack, and we have identified it and we've indicated to the user of this, although this is a programmer. So like I say, it's probably better to have a Boolean return value where you say true or false. Was this something? And that is push for a stack. Ridiculously simple. But the stack is crucial. Yeah, go on.
Do you have to have a loop?
There's no loop. No, it's just a single action, pushing one item. That's all it is. There's no loop. Yeah, I'm incrementing it there. When I push an item onto the stack, so if I was going to put another item onto the stack now, so 77, currently stack point is less than the length, so we're good to go. We can put something on there. So when I come to execute this, I'm saying, right, wherever the stack pointer is, put my item on there, and then increase the stack pointer, so it moves to the next free space. And that's it, and that end of operation. Okay? Oh, I've lost my top now. And that's it. And that's the pseudocode. You will get asked to be able to do this in the exam. But you can see, even if you can't remember that, if you draw yourself a diagram, dead easy to do again. Dead easy. So that's putting something onto the stack. So we check to make sure the stack's not full. If it isn't, great, we'll put something on. Make sure we update the values. Pop. To remove something from the stack. Right, looking at the state of the stack in this example, if I want to remove something from the stack, and the stack pointer is pointing to the free space, what have I obviously got to do with the stack pointer first?
Decrement it.
Yeah, decrement it. So my first action is going to be, and I'm going to do it here again because obviously there's things we need to worry about, SP equals SP minus 1. Decrease it. So let's just physically do that. So I'm going to go, decrease the stack. It's now pointing to the top item. So I can just return it. Return that top item, if I wanted to. So I could write, return, because I don't need to update anything, stack at the current stack pointer. Yeah? So when I come to push from this state, can you see what's going to happen? If I push a new item, where's it going to go? So if I push 54 now, I've just removed an item. Where's it going to go? What location?
It's going to go in 2.
No. It's going to go in 1. It's going to override.
Oh. So you just do.
Yeah, so if the stack is set up, the stack point is pointing to the free space. 77 has been removed. It might physically still be in memory, but as far as we're concerned, and this is how data structures work, the pointer's saying that's where the next item's going to get written. So if I push another item, it's going to go there. Overwrite. We do not go around deleting things from memory. Waste of time. We overwrite stuff. Okay? Which is why it's very important when we're programming to initialize variables. People get into this cozy little fuggy way of programming where they assume the compiler is initializing everything. The memory where all your stuff's stored. And most modern compilers will do that. Put default values in. But you can get caught out when you work in an environment that doesn't do that. Okay? If you ever have to do something where you're doing a little bit of assembly language because you want some speed, and you might come across situations where you do that, if you don't think carefully about initializing, you could be in deep trouble. Because the assembler won't initialize anything. Okay? Just like when we were doing that on my computer and you had to like make up 1.1 and you had to actually physically yourselves set a value, didn't you? If you wanted the number 1 for some reason, for incrementing or decrementing. Right, under what condition is the stack going to be empty? So when we're removing things, popping, when is the stack going to be empty? How are we going to be able to test that the stack has got nothing in it?
When the point is 0.
Can everyone see that? So if I remove this, the stack point is going to be there. Okay? That effectively means the stack has got nothing in it. Okay? If it's pointing at 0, it's empty. So we need to do a test. So if the stack pointer is greater than 0, then we can remove something from the stack. Else, now this is a daft thing because it's pseudocode. If we're returning the item on the stack, we have to return something. If we don't return an item on the stack, it's a function. You have to return a value. So we need to return something. I'm assuming it's numbers that I'm dealing with on the stack. Okay? Which in general, if it's a computer, we can interpret things as numbers. So we return -1, null, something that indicates that there is no value to return. You can, because it's pseudocode again, do output and explicitly explain to the exam board that the stack is empty. Okay? Obviously, if you try to implement that in code, it wouldn't work. Unless we were throwing an exception. We could, on that line, say, you know what, there's no point in this going any further, throw an exception. And the person using the stack would need to set their code up so that it can catch that exception by using a try-catch block, which most modern languages allow you to implement. So we can detect when the stack's empty, and then we can decide what to do. Okay? And again, that's it. It's simple. There is one other operation that might be useful with data structures, and that's to look at a particular location to see what is on the stack. And that's called peek. So peek basically is like pop without adjusting the stack pointer. We just look at a particular memory location. You need to check that the memory location is within the active part of the stack. Okay, right, there's two things you can talk about to do with this data structure. An array. How can we describe an array? What's the word beginning with S? An array is what type of structure?
Static.
Excellent. Static. It's static. Its size, and this isn't true in all languages, but its size is fixed when we design, when we write our code. We would say, right, okay, we're going to create a stack. Let that stack have 1,000 items. No more. That's it. So we can create an array. But what can you tell me about the stack structure? So the array is static. It's fixed size. What can you tell me about the stack?
It's dynamic.
Yeah, it's dynamic. It changes size, doesn't it? As we use it, it grows. As we remove things, it shrinks. It's dynamic. So we're actually implementing a dynamic data structure using a static data structure. Ooh, spooky. And you'll see this over and over again. Okay, we'll do this when we look at queues, we'll do this when we look at linked lists. Okay? But this is a fundamental data structure. It is this stack mechanism that allows us to call a function. Because when we call a function, what we do, we're changing the program counter in the CPU. If you think about the fetch execute cycle, the program counter says where the next instruction is. When we get an instruction, have you done the fetch execute cycle?
Yes.
Right. When you get an instruction, what do we do with the program counter? Increment it. So, as far as the CPU is concerned, executing a program is a linear process. We start at memory location 0 and we just keep going through. The majority of programs do not work like that. What instructions in Little Man Computer modify the program counter?
Branch.
Right. Branches. BRA, branch always, forces the program counter to a different location. Okay? So that allows us to do loops. If we want to call a procedure or a function, and we've got like a block of code that we want to execute, at this point, we might want to call a function. So we need to change the program counter to point to that function. But when it's finished, we want to come back to the next location in sequence. Yeah? The only way we can do that is if we record what that next location would be. So we need to put the program counter on the stack before we call a function. That's why we call it calling a function. Sometimes call it executing a function, but when we come down to low-level languages, most of the CPUs have got an instruction that is either jump to subroutine or call, depending on whoever decided what the assembler should look like. Okay, so when you execute a jump to subroutine, Little Man doesn't have this. Alright, jump to subroutine. What you're actually doing, this is after the program count has been incremented. So that you grabbed this instruction, the program count has been incremented, so it's ready for the next instruction in the sequence. But what this one says is, jump to 100. So the 100 goes into the PC. The fetch execute cycle started again, and because the CPU is dumb, it just carries on. So PC is 100, okay. It doesn't know that it was current before 50. It doesn't remember that because it's thick. The CPU is thick. Okay? It has no intelligence or whatsoever. It is dumb. It is unbelievably dumb. It just does the 7 steps of the fetch execute cycle over and over again. That's all it does. You could be on camera, Josh.
I don't think I am. We'll see the video.
We'll see. Right, so when we get to the end of a function, so a return, which is why functions moan at you if you don't put a return. It's going, oh no, there's no return. There's no return, it's broken, it's not going to work. When we get to the return, what happens, there might be some data that's passed back. We're not going to get bogged in with that. There's loads of different mechanisms for that. But we'll come on to that way later on. But what happens when we hit the return? We're saying, right, we're finished with this function. So we've got to do this bit. We've got to go back. So what happens is something popped from the stack and put into the PC. So let me just do this example. So let's say it was at location 49 and that was this. So that was at memory location 49. When I finish that function, I want to go to location 50. So what would happen on the stack? Let's assume the stack is set up like that currently. And this is the nice thing about the stack. It remembers things in the order they were dumped on there. So when I get to this instruction, I fetch it from memory. The program counter is incremented, and then we attempt to execute this instruction. So the program counter is currently 50, because it's been incremented. I go to execute this instruction. So before I overwrite the program counter with 100, I go, oh, let's just push 50 onto the stack. So we increase the stack pointer, oops, put the 50 in there. We can then overwrite the PC with 100, which is the operand for that instruction. So the PC then becomes 100. We start the fetch execute cycle again. Okay. That then says get an instruction at 100, which will be the first instruction of the function we've just called. We don't have to worry about this when we're programming high-level languages. We just put Dave, and it magically just runs the Dave function. Okay? We don't worry about this, but the compiler's having to do all this for us. Okay, so that gets executed. So it may be several steps, depends what that function's doing. If we've created an infinite while loop, we'll end up sticking our program. Okay, and we'll never come back from this function until we kill the program or whatever. When it gets to the return line, all we've got to do is say pop. And most assemblers will have an instruction, return from subroutine. And all that does is say, okay, take whatever's on top of the stack. So in this case, drop the stack pointer, read the 50, and put it into the PC. Start the fetch execute cycle again, and the CPU just dumbassly carries on executing, and it's back to our original program. This is fundamental. If you haven't got this stack mechanism, you cannot do function calls. That's not strictly true. You could do a really budgy way of recording what your return address might be. But when we're writing programs, we have functions that call functions that call functions that call functions. How many different return addresses would you need to store? How do you know what order to return? The stack does it all for you automatically. Okay? The stack is known as a last in, first out structure. That's what describes it. So the last thing into the stack is the first thing you remove, because of the way that push and pop work. When we get an interrupt in the fetch execute cycle, the same thing happens. Because you're interrupting the flow of a program, and it can happen at any time. So it's tested at the end of the fetch execute cycle. What we do is we go, ooh, got to handle an interrupt. In order to do that, I've got to run some code. So put the current PC onto the stack, update the PC with the interrupt handler's code, go and do the interrupt handler, and then when you've finished, pull the item on top of the stack. There are loads of implications with this. We'll look at this when we do some assembly language programming. Some proper assembly language programming. Okay, and you'll see how disastrously, if you're working at low level, how disastrously cocking the stack up can be. I had to bin 3 days of work on a project I was working on. I was writing a game, and I'd gone down a bit of a rabbit hole with my code, and I hadn't run it for a few days, and I was coding away, and I came to run it, and I'd broken it completely, and I was crashing the whole thing because the stack had gone out of control, and I couldn't for the life of me really see what I'd done. So I had to start again. In fact, I scrapped the whole thing and started from scratch again with all the great ideas I'd made. I learned a lesson there. I didn't have any previous version of it. I'd edited the original. So that's not a good thing. GitHub is the way to get over those problems. As long as you remember to push stuff to GitHub, which I forget to do sometimes. When you go, oh no, I haven't pushed to Git for a week. I've done a week's worth of changes. I've lost all my stuff. Okay, so this is fundamental to how our programs work. Yeah.
You know when you have
No, they don't return values, but procedures, you're still calling routines that are in other locations in memory, aren't they? They don't return, but they will end. Procedures do end, don't they? They just don't return a value.
So how would you return back to the original?
You would still have the same thing. The return mechanism, I haven't explained how that works yet. There are various ways. In Intel hardware, there is actually a register that you put your return values in. So the program that called the function looks at that register to see what the answer was, what was given back. But there are other ways of doing it. You can pass it through memory locations, all sorts of weird things. So don't get bogged down with that. So return basically, at the end of a function, says, here's a value that I've worked out for you, whatever the purpose of that function was. With a procedure, which is like this one, it still ends, so it's the same process. We just say, oh, when the procedure ends, take the top item from the stack, put it in the program counter, and carry on execution from that point. Now the funny thing is, when you're programming, you can put anything on the stack. So I could, as the first line of a function, have a push command. So in Z80, I might push the BC register, which is a 16-bit value, which is an address, just like the program counter is. If I did that at the start of my function, I would actually be altering the return address, fundamentally breaking everything. Okay? Again, these are things you don't worry about when you're doing high-level languages. You have to be critical of the stack. It's a shame that it isn't part of the course to truly do the assembly stuff, because you would learn a lot about the inner workings of the computer, which is why I want to do a little bit with you. Okay, so that is the stack. We will implement this at some point. Can you see that it's actually going to be quite trivial to implement? It's basic array work. That's all it is. Okay, right, I'll start the recording there.